Hello, friends. I am Satish Lele. I am a chemical engineer. I am working in the field of piping for the last 30 years. This video is part of my chemical process piping channel on YouTube. This video is about hot piping. Pipes for steam systems are commonly manufactured from carbon steel to AM10 16.9A106. The same material may be used for condensate lines, although copper tubing is preferred in some industries. For high-temperature superheated steam means, additional avoiding elements, such as chromium and molybdenum, are included to improve tensile strength and create resistance at high temperatures. Typically, pipes are supplied in 6 to 8 meter lengths. The pipes and fittings used are as per Boiler Regulation Laws Indian Boiler Regulation Act in India. The pipes are of seamless construction and stamped for use as steam pipe. Sizing pipes based on velocity. The velocity is an important factor in sizing of steam pipes. If a reasonable velocity could be used for particular fluids flowing through pipes, then velocity could be used as a practical sizing factor. As a general rule, a velocity of 25 to 40 meters per second is used when saturated steam is the medium. 40 meters per second should be considered as an extreme limit. Above this, noise and erosion will take place, particularly if the steam is wet. Even these velocities can be high in terms of their effect on pressure drop. In longer supply lines, it is often necessary to restrict velocities to 15 meters per second to avoid high pressure drops. It is recommended that pipelines over 15 meters long are always checked for pressure drop, no matter what the velocity. The chart shows maximum recommended flow rate in kilograms per hour, at velocity in meters per second for pipes of different MB at pressures in bar. The chart shows pressure drop factor for pipes of different sizes in MB at steam flow in kilograms per hour. This factor multiplied by length of pipe gives pressure drop in pipeline. Steam piping starts from stop valve of steam boiler, which is generally located on the top of the boiler. It is then carried to plant on pipe rack. On pipe rack, it is placed at the end. This helps in providing expansion loops. If the loops to be provided are above the pipe, the steam pipe is placed on upper rack. If a U-loop is provided below the pipe is located on lower rack. The shoe is provided to the pipe, wherever it rests on the structure. It helps in ease of installation of the pipe. Shoe is prepared by cutting an I-beam into 2 parts, and welded to pipe from lower side. Fiberglass sheets are the preferred insulation. Thickness of insulation depends on surface temperature of the pipe. An expansion loop is provided for every 8 meter pipe length for a steam pipe having diameter up to 100 mm MB or 4 inch MB. For sizes above 100 mm MB, loop is provided after every 4 meters or less. Generally, gate, globe, and plug valves are used to control flow of steam. Inside the plant, pipe is on close to wall with steel structure for proper support. Inside the plant, the direction of pipe is changed by 90 degrees, every 8 meters or 4 meters or less. The steam flow control station, which is placed firmly on the ground, is placed near the equipment. Condensate piping. The condensate from the equipment is removed by condensate pipe. The size of condensate pipe is smaller than steam pipe. The steam trap is connected to the end of pipe. condensate coming out of steam trap is collected in condensate tank and sent to boiler house. The flash steam from condensate tank is used in the plant for heating purposes. The first function of any steam trap is to remove air and non-condensable gases from the equipment to which it is assigned. If the air is not removed, steam will not be able to enter the equipment. Hence, heat transfer will not occur. If air is not removed as designed, you may get uneven heating among different components, poor steam distribution, and possible corrosion. The next job of the trap is to close in the presence of steam. The last job of the trap is to drain condensate. All steam piping systems must be designed so as to remove condensate from the steam line as soon as possible by the use of steam traps and drip legs. Drip legs collect condensate and are located at all low points in steam lines and at intervals in horizontal piping. The steam trap is connected to the drip leg and will open to allow the condensate to escape, then will close when it senses steam, thereby not allowing any steam to escape from the line. Strainers must be provided upstream of the steam trap to prevent any scale or grit from entering the trap and causing them to stick in an open position. Some traps have built-in strainers. Steam trap is located at every low point in the steam system. If there is a long horizontal run of pipe, as in a pit route, then it will be necessary to provide drip legs and steam traps at intermediate locations. The drawing shows location and arrangement of steam traps based on diameter of the steam pipe. Steam trap suppliers such as Armstrong and Spalax are extremely knowledgeable and offer excellent instructional information. Steam traps fall into three categories. Mechanical steam traps are of two types, which are ball float and inverted bucket. Thermodynamic steam traps, which are also called impulse or control disc. Thermostatic steam traps, which are temperature sensitive. Ball float trap works in the following method. On startup, a thermostatic vent allows air to bypass the main valve. As soon as the condensate reaches the trap, the lever mechanism opens the main valve. Hot condensate closes the air vent but continues to flow through the main valve. When all condensate is removed, the float drops and closes the main valve, which remains at all times below the water level, ensuring that the steam is not wasted. Inverted bucket traps. The inverted bucket is the most reliable steam trap operating principle known. The heart of its simple design is a unique leverage system that multiplies the force provided by the bucket to open the valve against pressure. Since the bucket is open at the bottom, it resists damage from water hammers, and wearing points are heavily reinforced for long life. Inverted bucket trap works in the following method. As condensate reaches the trap, it forms a water seal inside the body. The weight of the bucket keeps the valve off its feet. Condensate can then flow along the bottom of the bucket and out of the trap. When steam enters the underside of the bucket, it gives buoyancy and the trap rises. This positions the lever mechanism such that main valve snaps shut. The bucket will lose its buoyancy as the enclosed steam condenses and steam escapes through the vent hole. Once this happens, the weight of the bucket will pull the valve off its feet and the cycle is then repeated. Any air entering the trap will give the bucket buoyancy and close the valve and prevent condensate flow. The small vent hole in the bucket will leak the air into the top of the trap. Thermostatic traps. There are basic designs for the thermostatic steam trap, a bimetallic and a balanced pressure. Both designs use the difference in temperature between limit steam and condensate or air to control the release of condensate and air from the steam line. In a thermostatic bimetallic trap, it is common that an oil-filled element expands when heated to close a valve against a seat. It may be possible to adjust the discharge temperature of the trap, which is often between 60 degrees centigrade and 100 degrees centigrade. This makes the thermostatic trap suited to get rid of large quantities of air and cold condensate at the start of conditioning. On the other hand, the thermostatic trap will have problems to adapt to the variations common in modulating heat exchangers. Thermodynamic trap. The thermodynamic trap is a robust steam trap with simple operation. The trap operates by means of the dynamic effect of flash steam as it passes through the trap. Thermodynamic trap works in the following method. On startup, a steam pressure raises the disk, and cool condensate plus air is immediately discharged. Hot condensate flowing through the trap releases flash steam at high velocity which cools the low pressure area under the disk, drawing it towards the seat. At the same time, the pressure of the flash steam builds up in the chamber above the disk, forcing it down against the pressure of the incoming condensate until it sits on the inner ring and closes the inlet. The disk also sits on the outer ring and traps the pressure in the chamber. Pressure in the chamber decreases as the flash steam condenses and the disk is raised by the incoming pressure. The cycle is then repeated. The chart shows steam trap selection methods. Steam control station. A typical steam control station is shown below. It consists of two stop valves to block the flow for removal of the control valve for repairs. A bypass valve is also provided, in case control valve is out of order. Every low point in the steam line must be tracked and steam control sets are no exception. The drip leg must be located upstream of the upstream lock valve so it is still functioning while the flow is going through the bypass. Steam tracing. Pipelines carrying viscous fluids are frequently maintained at an elevated or operating temperature by means of steam tracers. These usually consist of one or more small bore steam lines running alongside the product line, the whole being covered in insulation. Steam tracing is also used as an alternative to electrical tracing in free